Welcome to the deep dive. Ever wonder how we actually use computers to predict something like a wave moving through a material?
Yeah, it seems straightforward, but it's surprisingly complex under the hood.
Exactly. So today, we're going to unpack a really key piece of research that looks right into that. The 1982 paper, Dispersion Analysis of Finite Element Semidiscretizations of the Two-Dimensional Wave Equation. It's by Robert Mullen and Belytschko.
Right, and this isn't just, some abstract academic thing. This paper gives really crucial insights for anyone who relies on simulations. Think engineering, physics, even acoustics. It helps us understand the built-in limitations, the potential inaccuracies when we model real-world waves numerically.
Like predicting sound in a concert hall.
Right.
Or vibrations in a plane wing.
Precisely. All those scenarios, the principles we'll talk about are fundamental there.
Okay. Because, we use these tools, these simulations, to make big design decisions, right? And to understand experiments.
Completely.
But what if the tools themselves are, subtly changing the physics? That's kind of worrying.
It is. And that's why understanding it is key.
So our mission for this deep dive is really to pull out the main findings on how these different finite element methods actually capture wave motion. Specifically, how good are they at getting the wave speed right?
Yeah, and how that accuracy changes depending on the digital grid, the mesh we use, and even the direction the wave is moving in.
Okay, let's get into it. What's the core problem they're tackling?
So the central challenge is something called dispersion error. When you use finite elements to solve wave problems numerically, you often find the wave speed in your simulation isn't quite the same as the real-world speed.
Okay, so the simulation wave travels faster or slower.
Exactly. That difference, that's the dispersion error. And it tends to get worse, more noticeable when your simulation grid is coarser, less detailed.
Or for shorter wavelengths.
Yes, exactly.
Yeah.
Short wavelengths relative to the grid size are particularly tricky. And this paper really digs into this specifically in 2 dimensions.
Right. And the mathematical starting point for all this is the 2D wave equation itself.
Yep. Ushto of a Q, 1C, 2011.
These two always go long.
Looks a bit intense, but what's it basically saying?
Well, U is whatever is waving like displacement or pressure. The equation essentially links how U changes across space, the x and u terms, to how it changes over time, the C term. And C is the key factor, the actual physical speed of the wave.
Got it. And they look at a specific type of wave solution to test things.
Yeah, they consider a plane wave. It's a fundamental type represented by U XBO. XB. Don't worry too much about the exact form, but it represents a wave traveling in a specific direction.
Okay, so you have this smooth, continuous equation, but computers need discrete steps, right? That's where finite elements come in.
Precisely, and that's the fascinating leap. How do you approximate that continuous behavior with discrete blocks? The paper looks at common element types like bilinear, quadrilateral.
These little rectangles.
Little rectangles, yeah. And also linear triangular elements, your basic triangles. These form the mesh, the grid that represents the physical space in the computer. And the shape of these elements and how you connect them actually affects how the waves behave in the simulation.
Profoundly. It's one of the core messages.
Okay, you mentioned choices. Let's talk about one, the mass matrix. The paper mentions consistent and lumped mass matrices. What's the difference there? Sounds technical.
It is a bit technical, but it's important. It's basically about how you distribute the system's inertia or mass onto the grid points, the nodes of your mesh.
Like assigning weight.
Kind of. A consistent mass matrix is derived more rigorously from the element mathematics. It sort of spreads the mass out, considering how it's distributed within the element.
Okay.
A lumped mass matrix is simpler. It basically just takes all the mass associated with an element and dumps it at the corners, the nodes.
Easier to calculate, maybe?
Generally, yes. But there's a trade-off. The paper points out that the errors you get with lumped mass are often about twice as large as with consistent mass.
Wow, okay, so that seemingly small detail can really impact your wave speed accuracy.
Absolutely. It's a key finding.
So how do they actually quantify this error, this difference in wave speed?
This is where it gets really interesting, like you said earlier. The heart of the paper is deriving and looking closely at the dispersion relation.
The dispersion relation. Okay, what is that?
Think of it like a formula or a relationship that tells you how the wave speed in your simulation, which they call EP.
EP for computational or phase speed.
J speed, numerical phase speed, yeah. How EP relates to the real speed, C.
Okay.
But crucially, it's not just CP versus C. The dispersion relation also shows how that relationship depends on the wave number that relates to the wavelength.
Shorter wavelength means higher wave number.
Right. And it also depends on the size of your mesh elements, like X or H.
So it's like a formula saying,
Yeah.
your simulation speed CP will deviate from the real speed C by this much, depending on how small your mesh blocks are compared to the wave and maybe other factors.
Exactly that. It quantifies the error based on the wave characteristics and the discretization parameters. It tells you how much your numerical speedometer is off.
And it reveals how things like the direction the wave travels relative to the grid lines also affect the speed.
Yes, that's a huge part of it, the anisotropy. The grid isn't usually perfectly aligned with the wave direction, and that matters.
Let's look at those quadrilateral elements, the rectangles, first.
Mhm.
They derived specific dispersion relations for these.
They did. For both consistent and lumped mass matrices. You can find them as equations 18 and 20 in the paper. But the figures 1 and 2, really tell the story visually.
Okay, what did they show?
They plot the ratio, CPC, the numerical speed divided by the real speed. Ideally, this ratio should be 1, right?
Meaning the simulation is perfect.
Right. But the plots showed this ratio versus a normalized wave number, Cox, which basically represents how many elements fit within one wavelength.
So higher values mean a shorter wavelengths relative to the element size.
Exactly. And what you see immediately is that CPC deviates from 1. The simulation speed isn't the real speed. And crucially, this deviation gets worse at higher wave numbers for those shorter wavelengths.
That makes sense. The grid has trouble resolving small details.
Precisely. But it's not just that. The plots also show the results for different wave propagation angles relative to the grid.
And the angle matters.
Oh, significantly. You can see the curves for different angles spread out. For some directions, the wave might speed up numerically, CPC1, and for others, it slows down, CPC1, especially for those challenging short wavelengths.
It's quite striking, isn't it, how much that direction relative to the grid influences the result.
It really is, and figure 2 drives home another point. The element shape, the aspect ratio of it.
So whether the rectangles are square or stretched out?
Yeah, if they're very stretched, high aspect ratio, that can make the dispersion errors even worse for short wavelengths propagating in certain directions. The geometry of your digital grid really starts to, well, warp the physics.
It shows how careful you have to be in setting up the mesh.
Definitely. And they also touch on something called underintegration.
What's that?
It's a numerical technique sometimes used with quadrilaterals to make the calculations faster, less computational effort.
Sound good.
But as figure 4 shows, it usually makes the dispersion worse. You trade accuracy for speed.
Another trade-off. Okay, what about the triangles? Linear triangular elements?
They looked at those too. Figure 5 shows a specific setup, a one-directional triangular mesh. Again, they compare lumped versus consistent mass.
And again, consistent mass performs better.
Generally, yes, the dispersion errors are smaller. The difference in accuracy is quite clear in the plots.
But triangles seem like they could be arranged in different ways, not just lined up.
Exactly, and that arrangement matters a lot. They introduce what they call the X triangular element mesh. Figures 7 and 8 show this pattern and its dispersion.
And what's special about the X mesh?
It leads to something quite fascinating. The appearance of different branches in the solution optical and acoustical branches.
Like different modes of vibration.
Kind of, yeah. Think of it as the mesh supporting different ways for waves to propagate, and these different modes have their own distinct dispersion characteristics. Their speed depends differently on the wavelength.
Wow, and there's even a cutoff frequency mentioned.
Yes, for the optical branch. Above a certain frequency or below a certain wavelength, that mode simply can't propagate through that particular mesh structure. It gets filtered out by the grid itself.
That's complex behavior just from arranging triangles differently.
It is. And then there's another arrangement they look at, the drum triangular element mesh, figures 10 and 11.
The drum mesh. Okay, different again.
Different again. It also shows complex dispersion, but the paper highlights a potential problem here. Spurious optical branches.
Spurious, meaning fake.
Essentially, yeah.
Right.
Artificial oscillations or wave modes that appear in the simulation but don't correspond to anything physically real. They're artifacts of the discretization of that particular mesh pattern.
So you could get noise or weird results that aren't actually happening in the real wave.
Exactly. The drum mesh, while maybe simple to generate, has this increased risk of numerical noise and these potentially misleading spurious modes. It really underscores that how you connect the elements matters just as much as the element type.
Okay, so let's try to pull this together. Comparing quadrilaterals and triangles, what are the big takeaways on dispersion?
Well, the first thing is that all these standard finite element methods introduce dispersion errors. There's no perfect solution among these basic types.
Right. The numerical speed is always going to be a bit off, especially for shorter waves.
Yes. But how it's off differs. Quadrilateral elements, especially bilinear ones, can work well, but their accuracy is quite sensitive to the aspect ratio, the shape, and the direction of the wave, particularly for those shorter wavelengths.
And consistent mass is generally better than lumped mass for accuracy.
Generally, yes, often by about a factor of 2 in terms of error magnitude, though it costs more computationally.
And the triangles.
Triangles, depending on how you arrange them into a mesh like the X or drum patterns, can show much more complex behavior. You get these different branches, cutoffs, and sometimes these problematic spurious modes.
So maybe potentially less predictable or requiring more careful analysis?
Potentially, yes. Table 3 in the paper is really useful here. It gives actual numbers for CPC for different meshes, different mass matrices, and different angles, all at one specific wave number. It lets you compare the performance directly.
Okay, so the big picture from this 1982 paper, which feels really foundational, is that the way we chop up a continuous problem into finite elements inherently messes with the wave speed.
That's a good way to put it. It introduces these dispersion errors, and understanding how that happens, how it depends on element type, mass matrix, mesh size, wave direction, wavelength, is absolutely critical.
For anyone running simulations, right, whether it's stress waves in mechanics or seismic waves or acoustics,
Absolutely. You need to grasp these characteristics to choose the right method for your problem, to set up your mesh appropriately, and crucially, to interpret your results. You can't just blindly trust the output. You need to understand its limitations.
yeah, this deep dive really highlights those subtle but really significant ways our digital models can drift away from physical reality. The choices matter.
They really do. Every choice in discretization has consequences for accuracy.
So thinking beyond this paper then, what should listeners be considering? How might these fundamental limits impact simulations we rely on today? Think about, I don't know, designing quieter cars or predicting earthquake effects.
That's the key question. These errors are inherent in the methods, so how accurate are our complex simulations in, say, structural dynamics or computational fluid dynamics where waves are involved? And what are people doing now to deal with this?
Are there strategies to minimize these dispersion effects? Better element types? Smarter meshes?
Yeah, that's a whole area of ongoing research. Things like higher order elements, special dispersion optimized methods, or adaptive meshing where the grid refines itself in tricky areas. Those are all attempts to tackle the challenges highlighted way back in this 1982 paper. It set the stage for a lot of later work.
Fascinating stuff. Definitely gives you a new perspective on those simulation results we often see. Thanks for taking this deep dive with us.